How you doing, guys? Welcome to another video. This is topic 4, volume 1, and in this volume we look at ionic bonding and structure. Let's get to it. So topic 4, volume 1, what is an ionic bond? And we look at the physical properties of ionic substances. IB understandings and applications all revolve around ionic, and some of these you've done in year 10 already, and some of them you might need to freshen up on, but we're going to stick to just going through those dot points and getting the key concepts. So an ionic bond, it exists between a metal and a non-metal. The metal is positively charged, a cation. The non-metal is a negatively charged anion. The way an ionic compound forms is metal atoms lose their electrons to the non-metal atoms to become positively charged cations. The non-metals, well, they gain those electrons and become a negatively charged anion. The ionic compound forms when large numbers of positive and negative ions combine in an infinite 3D lattice. This lattice is held together by strong electrostatic forces of attraction, which is described as the attraction between the positive and the negative ions, and that's responsible for the ionic bonding. In the models, we can see that the positive ions are surrounded by negatively charged ions, and the negatively charged ions are surrounded by positively charged ions. Because if they weren't that way, then they would repel each other, but they need to attract. At standard conditions, all ionic substances are solids. So when I have an ionic substance, I need to get a solid and then dissolve it up in water if I want it to become a solution. An ionic bond, again, forms when a metal loses electrons to the non-metal ions, and then there's a transfer of electrons and we have our ionic compound formed. We can show this using an electron shell diagram. So for instance, sodium wants to lose one electron, chlorine wants to gain one electron, so sodium will transfer its electron over to the chlorine to become a sodium cation and a chloride anion. Both of them are now happy, they both have a full outer shell. We could represent this using subshell notation. So the subshell notation for sodium, 1s2, 2s2, 2p6, 3s1. And then we add that to chlorine, Cl, its electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5. So that one electron from the sodium is going to go into the p subshell of the chlorine. We're going to end up with a positively charged sodium with the formula 1s2, 2s2, 2p6. And then we use a dot to represent that they are now bonded together. So we have dot, the chloride ion, Cl-, and its electron configuration will now be 1s2, 2s2, 2p6, 3s2, 3p6. Both of them have a full outer shell, and they're connected by the ionic bond, the attraction between the positive and the negative. To remember, we need to be able to work out the main group charge from elements in the periodic table. So very simply, things in group 1 want to lose 1 electron, things in group 2 want to lose 2 electrons, things in group 13 will want to lose 3 electrons. The noble gases, they don't want to react. Things in group 17 will want to gain 1 electron, 16 gain 2 electrons, and 15 gain 3 electrons. Remember that with the transition metals often have multiple oxidation states. So when we identify the state or the charge on one of the transition metals, we need to make sure that we write the Roman numerals if we're asked to write the name. A little bit of practice for writing formulas and writing names. Potassium bromide. Potassium is a positively charged ion. Bromide is a negatively charged ion. We can put those together so we have KBr. Magnesium sulfide. Magnesium is 2 positive. Sulfide is 2 negative. So they go together, MgS. Iron 2 sulfate. Well, iron 3 sulfate. So we have an Fe3 plus and an SO4 2-. They don't nicely balance, so we've got to find a common factor. Our common factor is 6, so we need 2 of the Fe's and 3 of the sulfates. The sulfates must go in brackets because we need 3 of them. If we're asked to write the names, B, that would be called potassium permanganate, the permanganate ion, MnO4-. For E, here we would have iron 3 phosphate, because the phosphate is 3 negatively charged, and if we need one iron, that means we need an ion with a 3+. If you could please go through and do the rest, that would be fantastic. Okay, let's talk about some of the properties. We need to be able to explain the volatility, electrical conductivity, and solubility of the ionic compounds. So we can use the structure of ionic compounds to explain those properties. The first one is volatility. Volatility is used to describe a substance that turns into a gas easily. Now, ionic compounds have low volatilities both as a solid and both as a solution. They don't turn into a gas very easily. That's because they have strong attractions between the positively charged and negatively charged ions, especially in the lattice. When they're dissolved, they have a strong attraction between the positively charged ions and the water molecules. So they're very hard to break that attraction. Perfumes, on the other hand, they have weak attractions between their molecules, so they are volatile, they turn into a gas easily. Electrical conductivity. In the solid, ionic substances do not conduct electricity in the solid state. That's because the ions are not free moving. There are no free moving charged particles in an ionic solid. So for something to conduct electricity, it must have free moving charged particles. Here, all of the electrons are in the ions and the ions are held together by the electrostatic attraction. However, if we melt that solid or dissolve it, those ions are now free to move. They're free moving charged ions. So sodium chloride, either melted, molten, or dissolved, will conduct electricity. The ions, we say, are now free to move, and that means that they can conduct an electric current. In the solution, those ions will be attracted to the oppositely charged electrodes. In the diagram on the left, those long solid bars, they're what we would describe as being electrodes. They're connected to a battery, and the battery has a positive and negative charge, and the ions, the oppositely charged ones, the positive will move towards the negative electrode, and the negative will move towards the positive electrode. We call that a migration of ions, and when we have an overall migration of ions, we say that a current is able to flow. So it allows that circuit to be complete and a current to flow. The high melting temperature of ionic solids is because of the strong force of electrostatic attraction between the positively charged ions and the negatively charged ions. And it takes a lot of energy to break apart that attraction. Therefore, ionic compounds are solids at room temperature. The melting and boiling points are generally higher when the charge on the ions is greater due to an increased attraction in the ions. So when we talk about melting point, we're talking about something going from a solid to a liquid. When we talk about boiling point, we're talking about a liquid to a gas. So the sodium chloride lattice, it melts at about 800 degrees, while the magnesium oxide lattice, it melts at about 2800. That's because in the sodium chloride, we have a singly charged ion, whereas in the magnesium chloride, we have a doubly charged ion. So that increased attraction makes it harder to break apart that lattice. Solubility refers to the ease which a solid will become dissolved in a solvent, a solution. And generally the solution will be water, the solvent will be water. What needs to happen here is there needs to be new bonds formed between the ions and the water. So when sodium chloride is dissolved in water, the sodium ions and the chloride ions become surrounded by water molecules. We say that they become hydrated. This attraction between the sodium and the water molecules, or the chloride and the water molecules, is known as an ion dipole attraction. The ion is the sodium, the dipole belongs to the water. When an ionic compound dissolves in water, positive and negative ions in the lattice separate from one another. The solvent is pulling apart the lattice, and we describe that as being ionization. Now, how does this ion dipole reaction occur? Well, water has a positive end and a negative end, and we call a molecule with a positive end and a negative end a dipole. So the positively charged sodium is attracted to the negative end of the water, while the chloride is attracted to the positive end of the water. So calcium carbonate is not very soluble in water. So what does that mean? Well, that means that the attraction between the calcium and the carbonate must be stronger than the attraction between the calcium and the water, or the carbonate and the water, because the water simply can't pull apart that lattice. So if you have a stronger attraction to the ions, you will be insoluble, whereas if you have a weaker attraction to the ions compared to water, you will be soluble. Now, to define an ionic bond, we can use the electronegativities to define when something becomes ionic. And ionic is uneven sharing of electrons. Basically, one is donating electrons and one is accepting electrons. So the difference in electronegativity, if it's above 1.8, then we say that the compound is purely ionic. So if we have magnesium oxide, we can state that that is ionic by looking at the electronegativities. The electronegativity of magnesium is 1.3. The electronegativity of oxygen, 3.4. So the difference in electronegativity is the difference between those two electronegativities, which is 2.1. 2.1 is greater than 1.8, so we can say that the type of bonding occurring by simply looking at the electronegativities is ionic. And ionic means that magnesium will donate 2 electrons, the oxygen will gain those 2 electrons. It is complete unequal sharing of the electrons, greater than 1.8 in electronegativity. Okay, volume 1, some top tips. Remember, ionic compounds are metal and non-metals. Make sure you can explain the properties using some of the key terms, especially the conducts electricity as a solution.